Hello everyone, welcome back. In the last class we introduced the force method. Let us continue with that today also. So today what we will do is, it is a lecture number 35. We will still continue with the force method. Okay. So what we have seen in the last class is force method is, in force method the redundant forces are taken as unknowns and additional equations are obtained by considering the displacement compatibility. Okay. So let us summarize the different steps that involved in force method, and the steps are, let us take this example, the same example that we analyzed in the last class. The first step is to, once we have any statically indeterminate structure and we need to solve it using force method, the first thing we need to identify what is the static indeterminacy of the structure, right. We know how to determine static indeterminacy for beams, for frames and for trusses as well. So, for this problem the static indeterminacy is 1, because we have on four reactions, 3 at support A and 3 at support A, 3 here and 3 here and 1 here. So, we have total 4 and number of equations available is 3. So, static indeterminacy for this problem is 1. So, first step is to identify what is the static indeterminacy of the problem. So, in this case it is 1. Then step 2 is, now once we know the static indeterminacy, then we need to we need to choose the redundant force or redundant moment. For instance, in this case static indeterminacy is 1. So, we need to find out what is the redundant force or what is the redundant moment. Okay. For instance, if we take redundant as support reaction at C, Cy is the redundant force, then what we need to do is, we can divide the structure into 2 parts. One part is this, where which is the remove the redundant force, and then this becomes a statically determinate structure, and then next part is apply on the same structure, now the structure is subjected to the redundant force, right. So, this plus this will give us this structure, that is linear, that principle of superposition. Now, in the same problem, instead of taking support reaction at C as redundant, we could take the moment at A as redundant. For instance, if we take moment at A as redundant, then what happened? Then the basic structures are, the first structure is we need to release that release the associated constant with the redundant. Now, if we take redundant as A, moment at A, then associated constant is the associated display is the rotation. So, we need to release that at point A. So, fixed support become hinge support. So, this becomes the basic structure, basic determinate structure, primary structure, very often it is called. And then plus the same structure is subjected to only the redundant force. In this case, the redundant in this case it is moment, redundant moment is Ma. So, again the principle of superposition says that this plus this is equal to this. So, this is step 2. Now, in any problem you can have say 2 redundant forces, the static indeterminacy is 2 or 3 or any number, depending on the number of static indeterminacy, we need to choose the redundant forces, and correspondingly you need to divide the structure and then add them to get the final response. Okay. Now, next is, once we have divided the structure into 2 parts, and both the parts are, you see, the determinate structure. Now, put a star here. Towards the end of this lecture we will see there are certain guidelines that need to be followed when we choose the redundant. We cannot, it's just that any force cannot be taken as redundant, any force or any moment cannot be taken as redundant. Okay, we will see that towards the end of this lecture. Now, so the step 2 is selection of redundant forces, right. Now, then step 3 is solution of the basic determinant. Now, in this case we have 2 determinate structure, because it is static indeterminacy is 1. Had it been 2, had it been multiple more than 1, then we could have several other small substructures as well. Now, in this case, we have two basic structures. One is subjected to the load, externally applied load, which is on the real structure, and the next part is the same structure, but now there is no externally applied load. Instead, this structure is subjected to the redundant force or redundant moment. Now, the step 3 is solution of the basic determinant structure under load. So, this is the basic determinant structure under load and this is the basic determinant structure under redundant force or redundant moment. Okay. Now, and similarly, if we take redundant force as this, and this is the basic determinant structure under load and this is the basic determinant structure under redundant force. Okay. Let us demonstrate step 4. Let us demonstrate step 3 with this example, this choice of redundant force. Okay. So, now solution of basic determinant structure. Now, this is the basic determinant structure. Now, we need to solve it, and this is the solution. Suppose under this load the beam deflects like this, and at point C, suppose it is delta CB. Please note the notation that we are using here. Delta CB means it is deflection at point C due to the load applied at point B. Okay. Now, then step 4 is, so this we already have seen in the last class that this delta CB is equal to this value. Okay. Now, this is again depends on your sign convention, whether you take negative or positive. Okay. Now, next is solution of basic determinant structure under redundant. So, under redundant, the basic determinant structure under redundant force is this. If we consider that Cy as redundant force, is a cantilever beam subjected to tip load, and it may deflect like this, and this is delta Cc. Again, please note the notation. It was delta Cb was the deflection at C due to load at B. Delta Cc is deflection at C due to load at C. And we have seen that this delta Cc value is Cy L cube by 3I. Okay. So, this is step 4. Now, the next step is using the compatibility condition at the release end. Now, in this case our release end is at C. So, what is the compatibility condition at C? Compatibility, what is the constraint at C we have? The deflection at C is equal to 0. Now, the compatibility condition says that then delta CB plus delta CC, so total deflection at C will be this plus this, that is the principle of superposition, and that should be equal to 0, that is the compatibility condition. Now, we know what is the delta CB, we know what is delta CC. If we substitute that, we get what is the value of Cy. The value of Cy is this. So, we had four unknowns here, 3 reactions at A and 1 reaction at C, and we could not solve using just equilibrium equation. Now, and then compatibility equation is used to have one more equation, and from that equation we could compute what is the value of Cy, what is the reaction at C. Now, once we know C, then how many then if it is a free body diagram of the entire structure, this is the last step. Last step you see here 3 reactions at A and 1 reaction at Cy. There are 4 reactions, we could not solve using equilibrium equation. Now, we have already solved we have already determined what is the value of Cy. Using the compatibility condition at C, and then once Cy is known, then we have 3 unknown. We have 3 equations: summation of Fx is equal to 0, summation of Fy is equal to 0, and summation of moments is equal to 0. And if we apply the equilibrium condition on this free body diagram, we can obtain the final solution. So, for last step is solve for the other unknowns. So, this will be the bending moment diagram, and this will be the shear force diagram, you see. And if you apply the equilibrium condition, these are the values that you may get. Please check these values. Okay. So, these are the steps that we follow in force method. Now, irrespective of the structure, it could be beam, it could be truss, it could be frame, it could be different, it can have different support conditions. The essence of these steps will remain same. Only difference will be the which depending on the static indeterminacy, you may have to choose the number of redundant forces and moments will be different, and then depending on the choice of redundant forces and moments, the basic determinant structures will be different, but the essence of the steps, they remain same for all the problems. Okay. Now, Before we go further, in the next week we'll be demonstrating this method. We'll be applying this method to different problems. Probably next week we'll apply these to plane trusses, and then next week we'll apply the concept of force method to beams and frames. But before we do that, this week the objective is to set the platform, right? To understand some of the to prepare the recipe, to understand the recipe for this method, okay, or each ingredient of the recipe. One of the very important concept in force method is flexibility coefficient. Now let's see what is flexibility coefficient. We are all familiar with the term stiffness. Now let us see, if we have a spring which is subjected to an axial load P, and then because of this load P, the spring undergoes deformation, and suppose the change in length is x, okay, and then we know that P is equal to Kx, where K is the stiffness of the spring, or sometimes it is also called spring constant, but the more general term is the stiffness, spring stiffness. Now, what is then the definition of stiffness? Definition of the stiffness can be written as P by X, and what it exactly? It is the force per unit deformation. So, it is the amount of force required to deform the structure. Now, you see here one important point is which force we are talking about and which deformation we are talking about. In this case, it is very straightforward, because you have just it is in one dimensional. It is just one dimensional, where you have force in one dimension, and in that dimension itself you have the deformation. So in this, at least for this spring, force is this direction and the deformation is in this direction, but you can have, we will see shortly, some of the problem where you are applying force at a point, but your associated deformation you are measuring at different points. So in that case, what could be the definition of stiffness? We'll see what could be the expression for stiffness, but as far as definition goes, it is force per unit deformation, and we'll see what kind of force and what is the associated deformation shortly. Now, if it is, then this is called stiffness, right? We are familiar with the term, and flexibility is essentially the inverse of stiffness, okay. At least by intuition you can say, without actually understanding what is stiffness, without really having the concept of structural analysis and solid mechanics. If you look at the term stiffness, the term stiff means which if we apply some kind of agitation, the structure is, or the object is very stiff, the deformation it undergoes is very less. Whereas we say the structure is flexible, means the deformation of the structure will be more if the structure is more flexible. Okay, so flexibility is the inverse of stiffness. And what is the definition of flexibility? Definition of flexibility is deformation per unit force. It is just opposite to this. Okay, so for this problem, what is the flexibility? The flexibility F will be using F to denote the flexibility. The F is equal to 1 by K, which is x by P, means it is the deformation per unit load. Okay. Now let us see, once we have defined flexibility, let us see what implication it has in the case of structural problem. Okay. So then similar to this expression, P is equal to Kx, we can express the same thing in terms of flexibility. X is equal to F into P. Okay. X is equal to deformation, F is equal to flexibility, and P is equal to the applied load. Okay. Let's see what happens. What is the interpretation of flexibility in the case of normal different structures problem. Okay. Suppose let's take two cases here. The first case, we have just now seen these two cases. These are the two basic determinate structure. This is the determinate structure under applied load, and this is the determinate structure under redundant forces. Okay, and suppose we are concentrating, as I just now said, that what is the force and what is the deformation. Suppose in this case the deformation we are talking about at C, I mean displacement at C. That is the displacement, that is the deformation we are focusing on. Okay. Now, delta CB, in this case it is delta CB, means it is displacement at C due to applied load at P, and in this case delta CC, displacement at C due to the applied load at C. Now, what we know is, just now we have seen that delta CB is equal to, the expression for delta CB is equal to this. Now, the same expression can be written as delta CB, the P is taken out and then this. Okay. Now, suppose this expression, the same expression can be written as minus P into FCB, where FCB is equal to 5L cube by 48 EI. Okay. Now, see in this case delta Cc is equal to PL cube by 3I, just now we have seen, and then delta Cc is equal to, write in a similar way, take P out and L cube by 3I, and this delta Cc can be written as P into FCC, where FCC is equal to L cube by 3I. Okay. Now, if we compare, just now we have seen that the relation between deformation, force and flexibility is x is equal to F into P, right, F into P, where x is the deformation, F is the flexibility and P is the force. Okay. Now, this term are called flexibility coefficients. Okay. Now, why you again please note the notations that we are using here. FCB is the flexibility coefficient, and this coefficient is associated with displacement at C and load applied at B, whereas FCC is the flexibility coefficient, where the load displacements are displacement at point C and the load is also acting at P. That is why it is FCC and it is FCB. So, whenever we talk about flexibility coefficient, similar as stiffness, then flexibility or stiffness, what they exactly do, they relate the displacement and the force, deformation and the load, right. Now, which deformation and which load we are talking about, depending on that, this flexibility coefficient will also change. For instance, in the same problem, in this we are measuring deflection at point C. Here also you are measuring deflection at point C, but in this case this is caused by load acting at B and this is caused by load acting at C. Therefore, their flexibility coefficients are different. So, this flexibility coefficient associated with this load displacement and this flexibility coefficient is associated with this load displacement. Okay. Now, let's see a more detailed, let us express this flexibility coefficient through another example. Suppose a simply supported beam which is subjected to a concentrated a moment at point A. Okay. And because of the moment, this is the deflected shape of the beam. The red line that you can see, that is the deflected shape of the beam. And the B is the point at the mid span. So, this is L by 2, this is L by 2. Okay. Now, theta AA is the slope at point A and delta BA is the deflection at point B. Again, please please see the notation. Why it is theta AA? Because it is the slope at A due to moment at A. Okay. Or and delta BA, why it is delta BA? It is deflection at B due to moment at B, at A. Okay. So, that is why it is BA. Now, this is a determinate structure. So, if you can solve this determinate structure, you will see that theta A is equal to ml by 3 EI. Okay, that we know how to solve it. You can use conjugate beam method or any other method to solve it and get what is the expression for theta A. It is ml by 3I. And now, if it is ml by 3I, then again it can be written as m into force into some coefficient, and this is equal to m into alpha AA, where alpha A is equal to L by 3I. So, what is alpha AA? Alpha AA is the flexibility coefficient, and this flexibility coefficient is associated with the moment at A and rotation at A. That is why it is AA. Now, we will be using two symbols for flexibility coefficient, one is F and one is alpha, F for displacement and alpha for rotation. Okay. Now, similarly for the same problem, what will be delta BA? Again we can find out the deflection at the midspan, and if you do that, then delta BA will be m L square by 16 EI. And again it can be written as m into FBA, where FBA is equal to L square by 16 EI. And what is FBA? FBA is the flexibility coefficient associated with the moment at A and displacement at B. So, displacement is this flexibility coefficient relates displacement at B due to the moment at A, displacement at B due to the moment at A. Okay. Now, again take another problem. So, these are flexibility coefficients. Okay. Now, take one more problem, take another case where the same simply supported structure, but now it is subjected to a concentrated load at the midspan. Okay. And the red line that you can see, that is the deflected shape of the beam, and the slope at theta is theta AB and deflection at B is equal to delta BB. Slope at theta AB means it is slope at A due to force applied at B. Similarly, it is delta BB is the displacement at B due to force applied at B. So, again this problem we can solve using any method that we learned in determinate structure, and if you do that, FA will be PL square by 16 EI, and then what will be the flexibility coefficient? Flexibility coefficient will be L square by 16 EI. Okay. Similarly, delta BB will be PL cube by 48 EI, and associated flexibility coefficient will be FBB will be L cube by 48 EI. So, in this case we can write that theta AB is equal to theta AB is equal to alpha AB into P. Okay. And similarly, we can write delta BB is equal to FBB into P. So, deflection is equal to flexibility coefficient multiplied by the load. Okay. Now, so this is again flexibility coefficient, right? This is also flexibility coefficient for these problems. Okay. And we are concentrating only on 2 points, one is at point A and point B. In this case, load is applied at A, and in this case load is applied at B, and displacements are measured at point A and B. Displacement means rotation at A and displacement at B, and the rotation at A and displacement at B. Okay. So, now what we have is, now suppose consider, now in this problem the loads are acting separately. In this it is only concentrated load, it is only the moment at A. Now, suppose we consider a problem like this, where the same simply supported beam, but it is subjected to both a concentrated load at the midspan and moment m at point A. Okay. Now, using the and these deflect like this, suppose, and corresponding rotation at A is theta A, and at B the displacement is delta BB. So, theta A, see, note here, in this problem we have not written theta AA or theta AB or delta. In this case it is not delta AB or delta BA or delta BB. When I write theta A, it is now cumulative action of M and P. When it is delta B, it is cumulative action of total action of M and P. So, theta A is the rotation at A due to both the forces, and delta B is the displacement at B due to their total action. Okay. Now, we know that using the principle of superposition, this problem can be divided into two parts. One is you remove the M, a simply supported beam subjected to P, and a simply supported beam subjected to M at A. Okay. Now, and this is M. So this is M. Okay. Now, so then this plus this should be equal to T. That is the principle of superposition, right? Now, just now we have expressed, we have seen the expression for theta AB, delta BB, and theta AA and delta BA for these two cases. Okay, and what are now? Then what principle of superposition says that if you are measuring displacement or rotation or moment at any point in this beam, that will be this plus this. Okay. So what will be theta A? Theta A will be theta AB plus theta A. Theta A will be theta AB plus theta AA. Okay. And now in this case, it is written, the absolute value is written here, but as far as sign convention, this theta is positive. So whether you write absolute value or not, it doesn't matter as long as you are concentrating on this displacement, this rotation. Similarly, delta B will be delta BB plus delta BA. Okay. Now suppose this is equation number 1 and this is equation number 2. Okay. This is equation number. This is equation number 2. Okay. Now, then what we have, these two equation, right? Then we have this equation we have, right? At delta BB that we have already obtained. Okay. Now, if we apply this into these two equations which we obtained from principle of superposition, then what we have? We have this theta A is this, theta AB is this, and theta BA is this, and theta BB is this. So we have these two equations. Suppose this is equation number 1A and equation number 2A. Okay. Now, then what we have is equation number 1A is this and equation number 2A is this, and in this equation alpha and F, they are the flexibility coefficients, associated flexibility coefficient, their expressions are this. Okay. Now, so if we substitute this in this equation, what we have, before that let us write this expression in a matrix form. So if we do that, then this is the matrix which have flexibility coefficients into M into P, M by P is equal to theta and delta, these are the displacement. Okay. Now, if you substitute this expression of flexibility coefficient here, then this becomes this. Okay. Now, so these, what we have done is now is if we consider only 2 points A and B, and these loads are acting on A and B, we are measuring displacement or rotation at A and B, then that displacement force, they can be related as this, right? And since we are concentrated, we have concentrated only on 2 points A and B. In this case, this matrix is 2 by 2 matrix, right? Now, this is called flexibility matrix. Now, you see, for a spring case, if you remember when it was a spring, we wrote that X is equal to F into P. Okay, it was just only one force, and in that direction only we computed the displacement, and therefore it is a flexibility coefficient, is a scalar value. But now what we have is in this case it is just not the one value, we have displacement, rotation, and those are at different points. Therefore the relation between force and displacement will not be a scalar relation, it would be a system of equation, and that system of equation written in this form, or the linear system of written in this form, and this expression is called flexibility matrix. Okay. Now, you will appreciate this way of writing the way of writing the displacement and the relation between force and displacement once we actually start analyzing different kinds of structure. Okay. Now, what is important here in this flexibility matrix, you see this matrix is symmetric. It is a symmetric matrix. it is a symmetric matrix. Okay, it is a symmetric matrix, and these values, this value and this value, they are same. Okay. Now, why they are same? You know why they are same. You have learnt, we have discussed the associated theorem which says that they are same, they should be same. Now, but we will not tell you in this class. Please think on that, why they are same, and if they are same, then what exactly they are telling about the effect of forces or effect of moment or in general effect of load on structure. We will discuss that when we actually solve this problem. But this matrix is symmetric. Now, your job is to check why this matrix is symmetric. Okay. Now, before we stop today, as I said that, choice of determinate structure is very important, because you cannot take, for instance, suppose you have a beam like this. You have a beam, is a simply suppose it is a hinge here, hinge, and then roller, and then roller. Okay, and this is an indeterminate structure, and what is the what is NS? NS in this case, NS will be two reactions here, one reaction here, one here, total 4 reactions, number of equations available 3, so NS will be 1. Okay. Now, what we need to do is we need to identify one redundant force and then divide the structure into some basic structure. Okay. Now, one you can do is, suppose identify the redundant force as suppose as this. Okay. If we can this is roller, this is roller, and this is roller, right? And then this plus we have taken redundant force as Fx. Fx is taken as redundant force. It is A, B, C. So, suppose I take Ax as redundant force. So, as per steps, this is the basic structure, and suppose it is subjected to any load like this P. Okay. So, this is subjected to any load P. So, first step is the calculation of NS, NS is equal to 1. Second stage is identification of choice of the redundant force, suppose our redundant force is Ax, and then divide the structure into parts depending on the value of NS, where the basic structure is subjected to load and the basic structure is subjected to redundant forces. Okay. So, it is basic structure subjected to load, and in this case it is basic structure subjected to redundant force. Okay. Now, then what you have to do, you have to solve this, and apply the principle of superposition and compatibility equation. But look at this, this structure is not, though here we have 3 reactions, here also you have 3 reactions, this is not a stable structure, because under the action of this horizontal load, this structure is not stable. Okay. So, it is not that you cannot take any force or any constraint as redundant. We have to make sure that whatever constraint or whatever force whatever reaction you take as or internal force you take as redundant, that will not lead to a system which are unstable. Okay. So, this is not the correct decomposition. What could be the better thing here? You take redundant force Cy as redundant force. So, if you remove the Cy, so this is your basic structure which is subjected to a load P here, and then plus again this is the basic structure and subjected to load Cy. Okay. Now, you see in this case it is a simply supported beam, it is determinate structure and stable, it is determinate stable structure. So, you can obtain the solution and then apply principle of superposition and compatibility. So, this is correct way of doing it. So, when you have any problem when you need to apply force method, then please make sure that the redundant forces or moments that you can take, that should not lead to a system which are unstable. This is very important. Okay, so we stop here. Next class what we do is we will introduce what is displacement method, and then once the displacement method is introduced, we move to we go to the next week to apply displacement and force methods for various structural idealization. Okay, thank you.